to a shape to make it better are to a large extent dependent on the intuition and the creativity of the naval architect who's involved with the project.
In spite of her enormous scale, the Titanic embraced many of the aesthetic design traditions of the 19th century. Her chief designer, Alexander Carlisle, had created a vessel that was pleasing to the eye, graceful, slender, and perfectly proportioned. Yet within the hull, she was a celebration of the technology of the new century. Perhaps her most advanced feature was a system of watertight bulkheads and compartments. It was this system that led the press of the day to bill the ship as the unsinkable Titanic. The system was designed to assure buoyancy even if the hull were to be accidentally breached by the sea. Buoyancy was a major concern of the Titanic's designers. They created its ingenious buoyancy system based on a very old idea. An idea as old, in fact, as Archimedes, the Greek mathematician who discovered the principle of displacement in 287 BC. One day when he stepped into his bath, Archimedes noticed that the water level rose in the tub. Within moments, so the story goes, he went running into the street naked, shouting, "Eureka! Eureka!" which in Greek means, "I have found it." The scientific law he discovered was this: a body partially or completely immersed in fluid is buoyed up by a force equal to the weight of the fluid it displaces. A cubic foot of water weighs 64 pounds. Suppose a cubic foot of wood weighing only 32 pounds is lowered into the water. Half the wood will sink into the water. Half will float above the water. If an object's density is greater than that of an equal volume of water, it sinks. If an object is less dense, it floats. It's not surprising, then, that a boat made of wood will float. But what of boats made of steel, the great liners, the Titanic? A cubic foot of steel weighs 490 pounds. Obviously, placed in the water, it would sink to the bottom. But if we were to hollow out the steel cube, most of its weight would be taken away. Now, the square foot of steel weighs only about 25 pounds. Since this is less than an equal volume of water, it will float. Now apply the same principle to a ship. It is a hollowed-out cylinder of steel weighing less than the weight of the water it displaces. And like Archimedes, like the Titanic, it floats. At the United States Naval Academy, there is a tank where such design principles as buoyancy and stability and soundness are put to the test.
The tank has been used historically since the late 1700s to refine the design of a ship. Back in those days, talk clipper ships, for example, a designer would have a design and an alternative design and would use the tank as a comparative means to choose between option A and option B. And as it started, it was simply a matter of tying a line to the front of a model, small model, and that line goes up over a pulley with a rock of a known weight on it. And when you let that rock go, the model goes down the tank. You tie the string to model B and you do the same thing, and whichever goes over that distance quicker has obviously got the less resistance to motion. So that would be the better design. Since that time, of course, electronics and our ability to measure things has gotten a lot better. And we now have incorporated in our tanks the ability to generate waves so that we can simulate the surface of the environment in which the ship operates, the wave system, measure motions, loads caused by waves. In our tank downstairs, we also have a wind generator, so we can simulate wind conditions for some of our normal-sized models up to 120 knots. You're dealing with probably, in many cases, the largest man-made engineered objects that you are going to put in harm's way, in the sense that you're going to put them out in the ocean where waves can get in excess of 100 feet tall and where winds can exceed 150, 160 knots. So it's like thinking about taking something like the Empire State Building, turning it outside, installing 200,000 horsepower, and wanting it to go anywhere in the world.
Getting a ship to float is one thing, but getting it to go where you want it to go, to move from one position A to position B, is another. It involves the mysterious science of navigation. As the Cheshire Cat said to Alice, you can't know where you're going if you don't know where you are.
On the night the Titanic went down, 2 course changes were made, certainly based on positions calculated by sextant fixes on known stars. It is ironic that these changes led the ship not away from the ice, but directly into its path. Of course, the technology that would have saved the Titanic was still on the horizon. It would be 10 years before scientists at the Naval Research Laboratory conducted their first experiments with radar. In 1911, just one human lifetime ago, when the Titanic was taking shape in Belfast, the only way to travel between Europe and America was by sea. The great shipping lines, Cunard, the French Line, the Hamburg-America Line, the White Star Line, all were competing for the millions of passengers eager to make the North Atlantic Passage. It was an enormously lucrative business. Millions of immigrants were flooding to America, and the wealthy of both the Old World and the New paid prime rates for the privilege of sailing a resort hotel across the sea. It was also a matter of national pride. Every maritime nation had to see its flag flying over one of these magnificent ships. After all, these were the pinnacle products of the Industrial Revolution. At that time, Cunard's Mauretania and Lusitania were the largest and fastest ships in the world. The White Star Line responded with the Titanic. It's sometimes difficult to comprehend just how large these great ships were. The Titanic, for instance, was longer than 3 football fields, twice as long as the Great Pyramid of Khufu is tall. If set on end, the Titanic would reach to all but the highest floors of the Empire State Building. Everything about her was of gigantic scale. The Titanic was a floating superlative, easily the biggest, most luxurious, most technically sophisticated ship of its day. William Garsky is a marine architect generally regarded as one of the world's foremost authorities on the Titanic.
It was the largest ship in the world at that time, although the Germans were building 3 ships that would actually be larger, the Bismarck, the Vaterland, and the Imperator. She was certainly a luxurious ship. She was built to carry the American millionaire at that time. The stateroom for first class and a luxury suite ran about $4,000 in 1912. Now, $4,000 in 1912 is quite expensive money, and when you can translate it to today's money. Other than what's new, the watertight doors might have been a little more of an advancement because the doors were actually activated when the water would reach a certain level and would close automatically.
To say that the Titanic was the first ship to have watertight compartments, I think, is an overstatement. Yes, watertight compartmentation is what allows a ship to be damaged at one part and yet maintain watertightness over the rest of it, sufficient that the ship will survive. And certainly at that time, the construction techniques were relatively new for large steel riveted structures like the Titanic.
It was precisely because of the Titanic's watertight compartments that the world perceived the ship as unsinkable.
To call anything indestructible is a little foolhardy. But as the Titanic came to design and finally to construction, as the largest, most modern in terms of technology vehicle that had come to pass, I think the excitement of it, probably from within as well as from without, and the people that were watching this all happen, led to the mother of all ships, and that's dangerous. We still are dealing with nature and an environment which can be terribly nasty. When you have something that you think is state of the art, there's a kind of a teenage invincibility that sort of takes over here. And if they had had a chance, the folks that were the operators of the Titanic had had a chance to sort of maybe sit back and think and not be involved in the euphoria, it probably wouldn't have happened. At the same time, I think some of the more mundane issues become overlooked when there's something so new and glitzy on the horizon, and in the case of Titanic, of course, the lack of adequate lifeboats.
There were some other things the Titanic didn't have on board when she sailed from Southampton on April 10th, 1912. For one, she didn't have any binoculars for her lookouts. Somehow they'd been locked away and the key misplaced. For another, she carried far too few lifeboats, only about enough for half her passengers and crew. The crew had never worked together before and were unfamiliar with the ship and her systems. Many wonder if the Titanic should have put to sea at all. She was a grand hotel, but was she a grand ship?
Dr. Charles Pellegrino is a marine archaeologist and author of the book, Her Name, Titanic.
When the Titanic was built, it was built largely under the idea that each ship was its own lifeboat. And actually, the Titanic, hitting the iceberg as hard as it did hit, and with all the damage that it did take along the side, that series of almost like Morse code punctures along almost 300 feet of the ship's length, was, it actually did quite well considering the kind of force of impact that it took. And it was just, I mean, just very strange piling up of one bit of bad luck against the next. The difference in whether the Titanic could sink or float was probably a matter of about 5 or 6 feet of damage. Plus everyone opening up the portholes on the starboard side of the ship and looking out, and a number of people leaving the portholes open as they left their rooms. Initially you had only about 12 square feet of damage to the ship. And it was a very, very well-built ship. It really was not an engineering problem. It was just incredible luck.
A boat is sort of another being in a way, and it's a living thing.